This is Unit 10, and it's chemical equilibrium. So equilibrium is when you have an opposite reactions happening, and they're happening at an equal rate. So rate means speed. So we're not saying that they happen with equal amounts, but they happen at equal speeds. So the forward reaction is going from your reactant to your product. The reverse reaction then is when your products reform your reactants. Now, it doesn't matter which direction the arrow is going. The stuff on the left is referred to as reactant, and the stuff on the right is referred to as products. So even though a reverse reaction, our products are reforming our reactants, we still keep the reactant on the left and the product on the right. We just change the direction of the arrow. Now, they happen at the same rate, so we can't see the change occurring. It's going to look like everything is remaining the same and there's no reaction taking place because we can't see the change. So that's what dynamic equilibrium is, when you can't see the change, but it is actually changing. So there's a YouTube clip that actually does a really good job explaining this.
A chemical reaction at constant temperature in a closed system is in a state of dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Dynamic means the reaction occurs in both directions. Equilibrium means there are constant concentrations of both reactants and products in the system. Consider a wet towel hung out on a line. High-energy water molecules can evaporate and are removed in the breeze. This continues until the towel is dry and can be represented by a simple chemical equation. This is an open system. If the wet towel is left in a closed sports bag, it does not dry. High-energy water molecules evaporate and remain as vapor trapped in the atmosphere around the towel. At the same time, low-energy vapor molecules condense on the surface of the towel to a liquid. The rate of evaporation exceeds the rate of condensation until the vapor becomes saturated. At this point, a balance is reached where the rate of evaporation equals the rate of condensation. A state of dynamic equilibrium is reached, represented by a double-headed arrow. Dynamic equilibrium only occurs in closed systems.
Alright, so dynamic equilibrium, you have the forward reaction at an equal rate as a reverse reaction, and we can't see the change take place. The law of chemical equilibrium says that our equilibrium constant K, or KEQ, or Kc, is equal to the products raised to their coefficients divided by the reactants raised to their coefficients. Now, it doesn't matter what reaction you're looking at, the products are always on the right and the reactants are always on the left. So you're going to take the stuff that's to the right of the arrow and place it on top, and the stuff that's to the left of the arrow and put it on the bottom. So if we use this reaction, we would have C and D on the top and A and B on the bottom, because reactants are on the right, products are on the right and reactants are on the left. Now, we don't include solids or liquids. So let's say D was a solid. D would then be erased from our equilibrium expression. If B was a liquid, we would also erase B because we don't include liquids or solids. So what is included? We do include gases, which we would symbolize by a G, and aqueous things, which is symbolized by AQ. So if it is a gas or if it's aqueous, it is included in the equilibrium expression. Now, when you calculate for K, if K comes up to be more than 1, then that means we have more products than reactants. If K is less than 1, we have more reactants than products. That also means if we have more products, then our forward reaction is favored. If we have more reactants than products, our reverse reaction is favored. A homogeneous equilibrium means that all substances in the reaction are in the same phase, so they're all gases or they're all aqueous. A heterogeneous equilibrium occurs when you have something in a different phase. So you might have a solid and two gases, or a liquid and two aqueous, or a solid, a liquid, and a gas. So heterogeneous, different phases, homogeneous, the same phase. All right, so for example, remember the words reacts with means plus, and to form is my arrow. So nitrogen gas, nitrogen's a diatomic, plus hydrogen gas, hydrogen's a diatomic, yields ammonia gas, which is NH3. You should be able to recognize that ammonia is NH3. So then we need to balance. 2 nitrogens, 1 nitrogen, we're going to multiply by 2. 2 hydrogens, 6 hydrogens, we're going to multiply by 3, and we're balanced. So the coefficient in front of the nitrogen is 1. If we divide the reaction in half, the stuff on the right is called reactants, and the stuff on the left is reactants, stuff on the right is products. So when I write my equilibrium expression, K equals product raised to the coefficient divided by reactants raised to the coefficient. Notice that there's no plus sign. We're not adding when we do equilibrium expressions, we're multiplying. Solid sodium bicarbonate decomposes into, so that is my arrow. So solid sodium carbonate, NaHCO3 solid, is my reactant. It's turning into sodium carbonate, cross your charges, solid, plus carbon dioxide gas, plus water vapor. So that would mean water is also a gas. So to balance it, I have 1 sodium, 2 sodium, so I put a 2 there. 2 carbons, and then 1 plus 1 is 2 carbons. 2 hydrogens, 2 hydrogens. 6 oxygens, 3 plus 2 plus 1 is 6, so we're balanced. Now this problem is different from the other problem because it's a heterogeneous equilibrium. So the stuff on the left is still called the reactant. The stuff on the right is still called products. But I have solids, and we don't include solids in our equilibrium expression, so we can cross those out. So K equals products. Now I don't need to worry about the solid, so we'll say CO2 times H2O divided by my reactants. Well, I crossed out my reactant because it was a solid, so I could just put a number 1 there to show that I don't have anything on that side. In number 3, to balance, I would need to put a 2. So it's homogeneous because I have 2 gases. So my equilibrium expression would be my product divided by my reactant. In number 4, it is balanced. It's a heterogeneous reaction because I have a solid and a gas. Solids are not included in the equilibrium expression. So I would just say products over reactants. In number 5, to balance, I would have to put a 2 and a 2. It's heterogeneous because I have solids and gases, and I don't include solids, so I can cross those out. So K would equal, I don't have any products, 1 over, carbon doesn't count, so it's just over O2. To determine the equilibrium constant, you write your equilibrium expression, then you plug in your equilibrium concentrations or pressures, So here's my reaction. It's homogeneous, they're both gases. So my K would equal the product over the reactant. And then I would just have to plug in my numbers. The equilibrium expression, or constant, sorry, is what I'm looking for. The product is what I put on the top. And I'm going to want to make sure that I square that value divided by the reactant. Now if you use one set of parentheses for the top and one set of parentheses for the bottom when you type it into your calculator will do the math in the correct order for you, and we would get 0.213 as our answer. If you do it step by step, the values might change a little bit. The answer might change a little bit. And number 2, notice that this reaction doesn't have any coefficients, so that means I would need to balance it. 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens. It's homogeneous, they're all gases, so I need to include everybody. K equals the product, NH3 squared, over the reactants, N2 times H2 cubed. So when I plug in my values, I'm going to want to make sure that my calculator squares the NH3 value, multiplies N2's value by H2 values cubed. So again, if you put one set of parentheses for the top, one set of parentheses on the bottom, you can type this in and get the value. So we would end up with 0.399 as our answer. Here we have a let's balance first. We have 1 oxygen, 4, 5, 6 hydrogens, so we would need to multiply by 3. It's a heterogeneous equilibrium, so I don't need the liquid. So this information about water is extra. So my equilibrium constant would equal my product divided by my reactants multiplied together. So K would equal 0.059 divided by 0.3 times 0.1 cubed. If you use one set of parentheses on the top, one set of parentheses on the bottom, your calculator will calculate this correctly. And we get a value of 197.